All right, geometry, lesson 43, we're going to talk about chords, secants, and tangents. These are all lines as they intersect or are associated with circles. So the diameter and a radius of a circle are two special segments. We should understand what a diameter is, right? It's a line that cuts through the center of a circle, and it goes from, it has its endpoints on the circle, right? Radius has one endpoint at the center of the circle, the other endpoint on the circle itself. Okay. Today we're going to add three more segments with different names, segments that are common to every circle. They are chords, secants, and tangents. A chord is a line segment whose endpoints lie on a circle. And there's, let's see, I think I've got it down here. Okay. An example of a chord down here would be segment AB. Okay. Its endpoints are on the circle. Okay. It begins and ends on the circle. Now, a diameter is also a chord, okay? But a diameter is a specific chord who goes through the center of the circle, okay? So all diameters are chords, not all chords are diameters. Does that make sense? Okay? So you can look at a chord that way, okay? A secant of a circle is a line that intersects a circle at 2 points. Basically, it's similar to a chord in that it does intersect a circle at 2 points, but it continues to go on, right? So it doesn't, think of it as the difference between a line segment and a line, right? A line continues to go on, whereas a line segment has endpoints. So a chord is a line segment with its endpoints on the circle. A secant is a line that intersects a circle at 2 points. Okay, and then we have a tangent. A tangent is a line that intersects a circle at 1 point. So it continues to go on in both directions, but it touches the circle on the circle at exactly 1 point. So it doesn't go through it, it just touches the edge. Okay, and I think that's probably the easiest explanation I can give for these things. I could read all of this for you, but does this illustration for you make sense? Okay. So you want to know the differences between those three things, and they'll have different component, special characteristics to them. Okay. These special segments can be used to find unknown lengths inside of circles with the help of the theorems presented here. If a diameter is perpendicular to a chord, then it bisects the chord and its arcs. Okay. So let's, drawing a picture here. All right, let's say if a diameter, okay, so here's a diameter, okay, there's the center there, okay. If a diameter is perpendicular to a chord, so I've drawn this diameter horizontally, all right. A horizontal line is always going to be perpendicular to a vertical line, so I'm going to draw it like that. If they are perpendicular to each other, then this diameter is going to bisect that chord just like that, okay. So if I see a diameter and a chord with a right angle, I know that that chord has been bisected. They may not show me it's been bisected, but I should know that because of theorem 43-1. Does that make sense? Yes, hopefully. Well, then the exact opposite is true, right? If they show me, I don't even really need to redraw it. If they showed me something similar to this right here, except all they showed me was that here's a diameter and here's a chord and it's been bisected into two congruent parts, then I know that this is a right angle. Okay, even if they haven't showed me the right angle indication, I know that it's a right angle because it's been bisected. Okay, so you have one that is a converse of the other. All right, if I know it's at a right angle, then I know it's been bisected. If I know it's been bisected, then I know they're perpendicular. Does that make sense? Okay, those two things work in comparison and contrast to each other. Okay, let's see if I can. I lost my cursor. Where are you? There you go. All right, and then theorem 43-3, the perpendicular bisector of a chord contains the center of a circle. Basically what they're saying there is if I have a chord, let's draw something a little different here. If I have a chord and I have a line that has bisected this and meets it at a right angle, then I know that this red line is a diameter. Okay? So now we're taking the two parts that we had from the previous two theorems. We're saying, well, now I know something about the red line. If they haven't told me it's a diameter, now I know it's a diameter if I know it's a perpendicular bisector to a chord. Okay? Does that help? Great. Okay? That could, and just so we're clear here, it could also be a radius, but a radius would contain the diameter. Okay? One final property of chords is that all chords that lie on the same the same distance from the center of a circle must be the same length as stated in theorem 43-4. So in a circle or congruent circles, chords that are the same distance from the center are congruent to each other. So if I draw a circle here and I've got a chord here and I've got a chord here, and here's my center, and I look at the distances between these chords, okay, and I see that those are the same length, they're the same distance away from the center, okay, then I know that these two chords are congruent to each other. Okay? Congruent chords are an equidistant from the center of the circle. So if I know that those two green lines are congruent to each other, then I know that they're the same distance from the center of the circle. Again, converse of each other. Okay, if I know one, then I know the other. If I know the other, then I know the one. Okay? That's it for some of that. Let's see what we can find here. Okay, we'll do a couple of these, and then we'll go to some of the stuff that's in your book for lesson 43. Okay? We want to find the length of x in the diagram. All right, so this line here, this, let's see, this blue line. Well, it's not letting me draw on it. Okay? Nope. Let's see if they give me nothing. Okay, so it won't let me draw on that. Let's see, the horizontal line, what kind of line is that? What do we call that line? It's a diameter. All right? What is the angle between it and the chord that it intersects? Maddie, what kind of angle are they meeting at? A right angle. Very good. If a diameter meets a, well, what do we call that vertical line there, Chandler? What kind of line is that? It's a chord. Okay, good. If a chord meets a diameter and they're perpendicular to each other, what is that diameter doing to that chord, Katie? Cutting it in half, bisecting it, right? So if one side of it is 3, then what do we know x equals? X equals 3. And it still won't let me write on it. That's okay. All right, so 3 is our answer there. All right, Marcos, we want to name a tangent line to the circle shown below, and we want to identify its point of tangency. Now, all of our theorems, we didn't really spend a whole lot of time with tangent lines. So before you answer, what do we know about tangent lines? How many places do they intersect a circle? Okay, looking through it. 1 point. Okay. Now, are they typically, mostly, are they on the outside or the inside of the circle? Outside. So what line is outside the circle but touches the circle at 1 point? Line AC. What is the point of tangency? B. Point B. And I would write all this up here, except for some reason I can't. So. Okay. Let's see. Katie. Measure of angle OYX. What is that? It's a right angle. Okay. Do you know why it's a right angle? So let's see if we can find a theorem or postulate in our book. And I think that theorem or postulate would be on page 282. Okay, what does 43-2 say, Katie? Okay, so it bisected this chord here, right? Because it bisected the chord, we know that they're perpendicular to each other, right? And you said that it was a right angle or 90 degrees or perpendicular. Any one of those three terms would have been appropriate. All right, so let's take a look at your homework at this point. Let's see if there, unless you see some questions in here that you'd like to go over, we can go over number 4 or 5. 4 or 5, probably 4. Do you want to look at 4 before we move on? Okay, it looks somewhat complicated. The circle shown has a diameter of 12 inches. And we see that with our line drawn across here. Chord BD is 8 inches long. How far is BD from the center of the circle? What they're asking for is we want to solve, and again, I can't for some reason write on there. Let's see if it'll let me do it. Maybe not. All right, so we want to solve for AC. Okay. Let's see. Notice that BD is 8 inches, right? So could I find out what the distance of BC is? What's the distance of BC? 4 inches. All right, so that's 4. Let's see. What is this BA line? What is that? It's 6 inches, but what would we name that line? The hypotenuse. Do I have enough information to use a theorem or postulate to find AC? What theorem or postulate would you use, Maddie? This is a triangle here, right? Okay, what type of triangle is it? A right triangle. So what theorem or postulate could I use to find a missing side length of a right triangle? You want somebody to help you out? It's like a weird guy's name. Pythagorean theorem. Do you remember what the Pythagorean theorem is? Okay. All right, Katie, you want to help us out? What's the Pythagorean theorem? A squared plus B squared equals C squared. Does that ring a bell now? Okay. All right, good. All right, do you know how these numbers would fit into that? Which one is going to be my C squared? The 6 or the 4? No. C squared is always the hypotenuse, right? So which side represents the hypotenuse? The 6 or the 4? The 6. The reason that is because of where it's located. It's located opposite the right angle. See this right angle here? Okay? Right? 6 is opposite of that, which makes it the hypotenuse. So we're doing, Michael, tell me what equation I'm writing here then to solve for AC. Okay, he said a squared plus 4 squared equals 6 squared, right? All right, and gosh, I wonder if I unplug this and plug it back in, whether or not it'll let me write on it. Let's try this. Okay, still nothing. Okay, all right, so 4 squared is 16, 6 squared is 36. All right, so you would take 36 minus 16. What's square root of 20? All right, what is the square root of 20? 4.47. Okay, and let's see if they give me any. Okay, let's come down to 4. Let's see if that's what they're looking for. 4.47 is what they're looking for. Okay? Now, on number 5, it says a chord of circle M passes through point M. A chord that passes through the center of the circle is called a what? A diameter. Okay? All right. So, let's take a look. Let's see. What was your assignment numbers? Okay. All right, so I am looking through. All right, let's see. Do you guys have question number 7 in your homework? Yes. Okay, so question number 7 in your homework says identify each line or segment that intersects the circle at right. Okay, identify each line or segment that intersects the circle at right. Well, that would be all of them, right? They all intersect the circle. Let me see if I can find another question in here from this lesson that you might need to see. What about question 15? Is 15 in your homework? Okay, so it says a circle has a diameter of 22 centimeters. A chord in the circle is 11 centimeters long. What is the exact distance from the chord to the center of the circle? But it doesn't draw you any kind of picture, right? I got to be able to draw this. This is what we're going to do instead, because I'm sure I can draw on this. Okay, so let's try this. Here we got a circle. That's a pretty good circle. Okay, a circle has a diameter of 22 centimeters, right? Right? Okay, so this is 22. Goes all the way across. Okay, and it says a chord in the circle is 11 centimeters long. Now I can put that chord anywhere I want, and because I can put it anywhere I want, I'm going to make it right here. Okay, because I can put it anywhere I want, right? Right? What would you make the angle where those meet at? A right angle. What would that do to this chord over here? Bisect it, okay? So that would take 11 and divide it by 2, right? That would make this little length here 5.5. Yes? Okay. Now what we're looking for is we're looking for this distance right here, correct? Okay? So we want to know what that is. Now, here's the thing, is that I could draw a line from here to there. Does anybody know what that length would be? What type of line is going from the center to the outside edge of a circle? No. Well, yes, but any line that goes from the center of the circle to the outside edge is a what? You're making it way more complicated than it needs to be. Any line that goes from the center of a circle to the outside edge is a what? Let me do this for you. Okay, so here's another circle. Here's a point, and I'm going to draw the exact same line, but without all the other lines. What would you call that? Oh, a radius. What is the relationship of a radius to the diameter? It's half. So what is this second red line I just drew? 11. All right. Now that I know that the hypotenuse of this triangle is 11, I know that one leg of it is 5.5. Can I find x? Yes. Okay. How would I do that? Okay, 5.5 squared plus x squared equals 11 squared. Okay, 5.5 squared, it's going to be what? 25.25? No, probably not. 30.25 plus x squared equals what? 121? Okay, subtract 30.25. Okay, x squared equals 90.75. Okay, and let's see, what question is this? This is you're saying x equals what? 9.53. It probably keeps going on, right? It's probably an irrational number. Okay, so you rounded. Now their answer they use is they say what is the exact distance from the chord to the center of the circle. So they're looking to solve this in simplified radical form. Trying to figure out how exactly they went about doing this. I want to know how they knew that this was going to be a special right triangle. And I think what they ended up looking at, what is 5.5 radical 3? Just check it for me. What's 5.5 times radical 3? Okay. So what, no, so what they're saying is that this is a 30, 60, 90 triangle, but there's nothing about this that actually says that. I would probably take 9.53. They're getting for their answer 5.5 radical 3. But you'd have to notice the relationship between 5.5 and 11. Oh, I think I see how they're doing this. Because if this 5.5 is double 11, right? Okay, so this would have a relationship of 1 to 2, which would make this a 30-degree angle. This would make this 60, right? Because it has a relationship of 1 to 2. Okay? Right? And if it has a relationship of 1 to 2, then it's going to be 1, 2, 1 radical 3. Does that make sense? If you remember your 30, 60, 90 ratios, which would make that 5.5 radical 3 because of the 60. Right? You're going to take your shortest side, which is your 5.5, and multiply it by radical 3. I'm probably, because you guys aren't going to be as adept at that, would still be willing to accept 9.53. Okay, but do you guys see how you can draw some lines that they're not telling you about because you know something about radiuses where you can make some right triangles that they're not drawing for you? Okay, so this is your answer for number 15. I don't know, I'm trying to see if there's any others. I think the only other one that shows up is 29. And so I think 29 is similar enough to number 15 because it says find the distance from the center of a circle with a diameter of 2.6 inches to a chord that's 1.2. You use the exact same process here. Okay? You draw your diameter, you make your chord a perpendicular bisector, right? You draw a radius to the end of that chord. Okay, does that make sense? All right, and you solve for x the same way you solved here. It may not be a 30, 60, 90. I think that they're looking for a decimal answer in that case. So, but you're going to draw the same type of picture. Okay? All right, so I'm going to end right there.